In our previous video, we looked at electrochemical cells, and we said that they are basically a way of conducting redox reactions in two separate compartments. So our standard experimental setup is to have two beakers set next to each other with a salt bridge, which can be a piece of string or a U-tube with the literal U-tube, the tube that looks like a U, filled with a substance that contains ions that don't react with anything. Usually it's potassium nitrate or potassium sulfate. And we can set that tube up and then connect the two strips. There are metal strips in aqueous solutions, and we can hook those up to a voltmeter or a light bulb, and we can measure a voltage, or we can drive a bulb or a phone or whatever else, because this is essentially a battery. We saw in our previous video that the observed reaction, if we construct an electrochemical cell composed of copper sulfate and copper wire, or copper metal, zinc sulfate, zinc metal, that the observed reaction is exactly the same one that we would observe if we were to put copper sulfate and zinc together in a single beaker. And so what we need now is a way to predict that this is in fact the reaction that would happen. And there is a way to do this. We look up values that are known as the standard reduction potentials, and there's a table of these that if you don't have it, you can look this up on the internet. And the table is always going to be consisting of reactions in the reduction sense. In other words, remember that Leo the Lion says Gur, gaining electrons is reduction. So we're always going to be gaining electrons in these tables, and we're going to be given these reduction potentials over here. Now you know that from redox, remember that redox stands for reduction and oxidation, and that both processes have to happen at the same time, because what is oxidation reduction? It's the exchange of electrons. Up here, our copper is gaining 2 electrons, our zinc is giving up 2 electrons. You always have to have one thing being reduced and one thing being oxidized in these processes. So one of these has to actually get oxidized, and it turns out the one that matches the observed reaction is always the one such that when we flip it and flip the sign of the reduction, that we get a positive number when we add them up. Okay, so that's a lot of words, so let's see the process. If instead of oxidizing the zinc, if we were to, reduce the zinc, if we were to instead oxidize it, that would make this reaction go the other direction, and that would flip this E naught reduction into an E naught oxidation, and that would now be a positive 0.76. This would match what we actually see happen in the reaction up here, right? I haven't noted my zero charges down here the way I did up here, but now I have. So the zinc is in reality being oxidized. So in our when we look at our reduction potentials, we flip that one around to be oxidized, and it's going to turn out that that's going to add up to a positive overall E naught, and that E naught value is going to be 1.0 volts, which you can't really see it, but I tried to draw that up here on my voltage meter, that this sum of the E naught red and the E naught ox, in other words, the reduction and the oxidation potential, adds up to the overall cell potential. And that's the same when the two half reactions from our potentials add up. This will always add up to be the correct reaction if and only if E naught here is positive. So it's going to turn out that E naught being greater than 0, in other words, positive, is always going to be our requirement for the use of the oxidation reduction potentials. So every time you have a given reaction, you're going to look up the reduction potentials that are associated with the things that are actually in your cell, and then you're going to flip one of them such that when you add them together, you get a positive E naught value. And that's how we're always going to be able to predict the outcome of an electrochemical cell.